So now let's consider a real problem or a problem that with some context. Suppose there is a retailer selling products 1 and product 2. Let's say the prices are P1 and P2. So these prices affects the demands. For product I, the demand is denoted as Qi, and let's say it is in this function. So P1 and P2 affects Q1 in this way. Q1 would be A minus P1 plus BP2. And Q2 would be A minus P2 plus BP1 according to this general formula. So what does that mean? That means when you increase your product 1's price, the demand would go down. But when you increase your price for product 2, whether there is an impact on Q1 depends on the parameter B. So here, the parameter B is assumed to be within 0 and 1 and cannot be 1. So somehow it's positive. If positive, what does that mean? That means when your P2 goes up, that's going to increase the demand for product 1. Well, does that make sense? I think in many cases that makes sense. Suppose product 1 is Coke and the product 2 is Pepsi. Okay? Then in that case, if your Pepsi is sold at higher prices, your demand for Coke would be increasing. So I hope that makes sense. You may also think product 1 as milk, product 2 as, for example, water. So if the two things are somewhat substitutes, then their demand would be affected by the price of the other product. For milk and the water, they don't be that so similar. Also, maybe that B would be small, but not 0. Okay? But for Coke and Pepsi, the B would be somewhat higher. Alright? So let's assume you know all the numbers. It's just that you now need to do some optimization. So what's the thing that you want to do the optimization? You want to set P1 and P2 according to your knowledge on A and B to maximize your total profit. And to make our life easier, let's assume there's no production cost. Okay, so now we have several problems to do, or we should say we have several steps to solve the whole problem. We want to first ask whether the parameter makes sense. Okay, why we set B to be within 0 and 1. And then we want to formulate the problem, check whether it is a convex program. Somehow it would be, otherwise we have no way. And then try to solve the retailer's problem, and then find an optimal price change according to the change of A and B. So let's try to do this. The first thing is that we want to argue it makes sense to set B to be within 0 and 1. So B somehow cannot be greater than 1, because in that case, the other product's price would have an even higher impact than our own price, which I don't think makes sense. For B less than 0, somehow it's possible, but in that case, your two products would be complementary instead of substituting. So the two products makes more useful things if they are purchased together. Okay, so like toothpaste and the brush that you may use to clean your teeth. So in that case, the two products should be purchased together. So if one thing gets more expensive, then the other thing would also get a negative impact, like milk and cereals. All right. So that's some cases that we may focus in the future, but today we only want to focus on substitutes. All right. So that's one thing. And then if we want to formulate the problem, I think it would be this one. So we want to choose P1 and P2 to maximize the total profit. For product 1, P1 is the price. And once you determine P1 and P2, this is the demand for product 1. For P2 is the same thing. P2 would be multiplied by the demand for product 2. So you may see that when we choose P1 and P2, they are really connected because P1 and P2 together determines Q1 and Q2. So we want to solve this problem. We want to first check whether it is a convex program. So let's say f of P is the negation of our objective function. Why is that? Because for this function inside a maximization problem, we want to check whether it is concave, but we don't know how to check concavity. So let's make f a negation for this objective function. Then all we need to do is to check whether f is convex. Okay? So actually there is also a way regarding the Hessian matrix to check whether a function is concave. It say that a function is concave if your Hessian matrix is negative semi-definite. But I don't think we need to bother to introduce that again, because all you need to do is to get the function's negation to check whether it is convex. So for this one, you may double check that your Hessian matrix will be looking this way: 2, negative 2b, negative 2b, and 2. The first leading principal liner is 2, so that's okay. For the second one is 4 minus 4b squared, which is 4 times 1 minus b and 1 plus b. Okay, so somehow this guy would be always non-negative if we have b within 0 and 1. So I hope that makes sense to have this assumption again, because this assumption actually gives the problem a nice behavior so that it is positive semi-definite, so that this function is a convex program. So f is convex, negative f would be concave. We are maximizing a concave function, and that's why our problem is a convex program. Okay. And then now all we need to do is to look for the gradient for our objective function f. So the gradient would be 0, and that means we need to have this one and that one. Technically, what we need is that our gradient of negative f should be 0, but somehow it has nothing, no impact, because whether you have the negation there is useless if you are talking about equaling to 0. So somehow we need to again solve some 2x2 systems. And then very quickly, if you solve these two systems, you would see your P1 and P2 must be A over 2 times 1 minus B. Okay, so maybe you need some hint about how to do this. Well, that's not too difficult. For equation 1, you know P1 must be A plus 2B P2 over 2. Alright? And then all you need to do is to take this, plug in to your second equation. Then you're going to get P2 in one equation. You're going to see that P2 would be A over 2 times 1 minus B. And then you plug in that again, you will see P1. So that's how we solve this problem mathematically. But the last thing we want to do is to get some managerial implication from this solution. So our solution is A over 2 times 1 minus B. We can see that this quantity increases in A. Okay, what does that mean? A is the original demand. So A minus P1 plus B P2 is the demand for Q1, right? So if A is larger, somehow that means our product is more popular and the base demand is higher. So when the product becomes more popular, most people want to buy it, you will set a higher price. That makes sense. For B, the impact of B is also positive. When B goes larger, what does that mean? Somehow when you increase P2 by $1, that's going to have a better or huger or larger impact on product 1. And the other way is also true. So when B is larger, it makes sense because the effective demand Q1 and Q2 tends to be larger. And if you have a higher demand, you somehow should set a higher price. So collectively, that's the whole process. Given a function or a problem, now we may formulate the nonlinear program, we may analyze its convexity, we may solve it through first order derivatives, second order derivatives, first order conditions, and then lastly, we may do some interpretations. This helps us to understand your problem and to understand your solutions. So pretty much we are done for today. Maybe you still have some questions in mind. For example, well, all these problems do not have constraints. How do we deal with problems, nonlinear problems with constraints? That would be the main focus for our next lecture. In the next lecture, we will tell you, well, indeed, there are some situations that you do have constraints. There are some ways that we may deal with them. Let's do it in the next time. Okay, so that's pretty much I have. Thank you.